Hello! Welcome IB Physics students, and we are still in Astro in the higher level part, only for you higher level people. And we're talking about stellar evolution, being about how little baby stars will form into protostars, and then how they will die and be dead. As all good physics students should know, all stars are powered by fusion. But that just starts out. You've got this big cloud of gas, and the gas is going to be of a certain temperature. And if there's not enough gas, that temperature and outward pressure is going to defeat the force of gravity and just hangs out. But if enough gas forms, gravity gets strong enough, and it starts to fall inwards, and that gravitational potential energy gets turned into temperature, and eventually the temperature goes up, pressure is going to start to go up, and you'll end up with extra heat and pressure. And if you get enough heat and pressure on a simple gas like hydrogen, then you can have a protostar, and fusion starts to happen, and bling, this giant cloud of collapsing gas turns on, and you get what we call a protostar. Now, you can have hydrogen fusion into helium fusing into carbon. Eventually, more and more complicated stuff can be built. And if you want to know which stuff is going to be built by a star, you look only at the mass of it. And more massive stars can make more complex elements through fusion. And you need to know a few of those types. One simple one is called the proton-proton cycle. And that is if you take 4 protons, or hydrogen atoms, I guess, or hydrogen nuclei, slam them all together, you're going to get this situation here. And you may not need to memorize the equation, but you should be familiar with what's what. You know this is a hydrogen atom. This here is a helium atom. This here is a positron. Very little mass, but the same mass as an electron, but a positive charge. This guy is being represented, that's a neutrino. And this guy here is a gamma particle. That's what's happening within our sun most of the time. Now, also possibly happening within our sun, you might have the triple alpha process. It's not some sort of crazy Greek fraternity from Revenge of the Nerds, which would be cool because I love that movie. Instead, these are helium atoms or alpha particles. 3 of them can be fused together to make carbon. Now, it is more complex than that, but that's the gist of it. Now, as you get even more massive stars, bigger than our sun, they can start fusing things together and start doing silicon burning. And that's basically where you start taking elements such as carbon and you slam an alpha particle into it. And you make a bigger atom, like, I don't know, maybe nitrogen. Then you slam another alpha particle on it, and you get a bigger element. Then another alpha particle and a bigger element. And eventually, you can get up to the big things like iron and nickel, etc. After iron, it becomes energetically unfeasible to do that anymore. Within the complex social order of stars, all the stars care about amongst each other is how much mass they have, because mass determines everything. How they're born, how they die, what elements they make, and also how luminous they are. You want to remember that luminosity is power, or how many watts that they have. And you can remember that luminosity is proportional to mass to this exponent here. Now, this is a stupid formula the way it's written because the fish symbol is proportional to, and they also use the fish symbol or the alpha as the exponent. I don't know why, it's dumb. But that alpha symbol here is going to be somewhere between 3 and 4. Now we can just put some numbers in here. If we assume that these are solar masses, mass of the sun, it would have a luminosity of 1 solar luminosity, I guess you could call it. If we had 2, and let's assume that this alpha particle was 3, 2 to the 3rd power would be 8. So let me just put some numbers on here. 6, 10, 20, 30. 2 would be 8. 3 masses to the 3rd power would be 27 times the luminosity of the sun. And as stars get more massive, they get incredibly more powerful. And so all those awesome stars out there that are bigger than our sun, they're not just a little bit bigger, they're crazy more powerful. We need to always remember that it's the mass that determines everything for a star, especially its death. And that's what we're talking about here is based on the mass of a star, always in relation to our sun is usually the easiest way to think of that. If you have a star that's less than a quarter the size of our star, anywhere from a quarter to 4 times the mass of our star, our sun, and even 4 to 8 times, you're going to get the same death. It's going to turn into a white dwarf, which basically it's going to blow up, swell out to a red giant, and then it's going to eject some of that outer stuff, not in a nova explosion, but it is going to eject it into what's called a planetary nebula. And that planetary nebula is nothing to do with planets whatsoever. It's just ejecting that outer stuff, and it turns into this white dwarf, which is basically the core that's left over, where there's no more fusion. It collapses in and gets really white hot, but it's done with its fuel source. It's just going to become a brown dwarf and then turn into a black dwarf over billions of years. If the star is between 8 and 40 times the mass of our sun, you get a giant supernova explosion, and it slams the core into a neutron star. And if it's bigger than 40 times the mass of our sun, which is crazy big, it will go through a supernova, slam the center into a neutron star. It continues contracting into nothingness volume-wise, but it becomes a black hole, which is some crazy stuff. Now, the Chandrasekhar limit here, something needs to be remembered, as 1.4 times the mass of our sun, if the core is less than 1.4 times the mass of our sun. You get that white dwarf. Now, the white dwarf is going to contract as far as it can, and then you have this electron degeneracy pressure, where the electrons can't occupy the same state as another electron, which keeps it from contracting anymore, although it is way crazier dense than any element you've ever seen or felt here on Earth. If the collapsing core after a supernova is between 1.4 and 3 times the mass of our sun, then you get the neutron star. With this upper thing, 3, being the Oppenheimer-Volkoff limit. Oppenheimer you may have heard of before, as far as he was the in charge of the U.S. atomic bomb. He's a physicist, super thin guy, always smoking a cigarette in every picture that's ever been shown of him. And if it's bigger than 3 times the masses of the sun, then you get, it'll collapse into a black hole. The neutron star, just so you know, can't contract anymore because of neutron degeneracy pressure. Basically, all of the protons get slammed into the electrons and they make neutrons. So you've got a substance completely made up of neutrons, and each neutron can't occupy the same quantum state as the other neutrons, whatever that means, and it can't collapse anymore unless it is this big, and then it turns into a black hole. If the IB is ever asking you, what is going to be the final stage or the death stage of any particular star, it's always going to relate to what mass the star starts out with. And you're only going to have 3 choices. All stars that I can think of anyway are going to end up as a white dwarf, a neutron star, or a black hole. All of them start out as a proton star, a little baby star, actually a giant gas that collapses into a proton star. It is going to go into the main sequence, and then, based on its mass, if it's less than 8 solar masses, sun masses, it goes up to make a normal red giant. Planetary nebula, not a supernova, it just sort of ejects some stuff as the core collapses, and then a very boring white dwarf with no more fusion happening, and it'll cool down. If it's greater than 8 times the mass of the sun, super red giant, and then supernova. Everything is super. It makes a super neutron star. No, it's just a regular neutron star, held up by neutron degeneracy. But if it's even more massive than 40 times the mass of the sun in its initial stage, then it can become a supermassive black hole.